We know how to do gram mole atom and gram mole molecule conversions. We've already learned that on a few videos that were posted earlier. Sometimes we'll get a question that gives us a certain amount of a substance, like let's say 50 grams of sulfur trioxide, and it wants to know how many oxygen atoms. So sometimes we'll get a problem that asks us for a very specific atom within a molecule. And I call that more of an advanced gram mole molecule problem. Had a lot of questions about this because my students had this on a recent review packet. So I'm going to go over a couple of these with you and just show you how to actually break a given mass of a molecule into a specific number of atoms. The good news is it's really just one extra step. So the skills needed to do this are, number one, you need to be able to write your chemical formulas. You need to be able to calculate molar mass. You need to be able to do gram mole atom or gram mole molecule, more specifically, conversions. And remember, that's just where we write down the given. We go from gram to mole using the molar mass of that molecule. And then we go from mole to molecule because there's 6.02 times 10 to the 23rd molecules per mole. Those three steps are going to stay the same, not going to change. We're just going to add a very quick, very small step to the end of these problems. So I'm going to do two, then I'm going to give you the opportunity to do one. I'll go over it with you, and really that's probably all it's going to take, and you'll never have trouble with this again. So let's take a look at the first one. And this question says, how many oxygen atoms are in a 50-gram sample of aluminum sulfate? So what we're going to have to do is, we already know, okay, they gave me grams of aluminum sulfate. So the first thing I would do is figure out what the chemical formula is for that. I've got to have that because I'm going to need the mass. So aluminum sulfate is an ionic compound. It is a metal crisscrossed with the sulfate polyatomic ion. So right here, we're just going to go and take care of that. We know that aluminum is +3. We know that sulfate is SO4 -2. When we crisscross, we get Al2, and then in parentheses, SO4 3. Now, before I can go any further with this problem, really before I can even start the problem, I'm going to have to find that molar mass. And just in case you haven't seen that video yet, out here to the side, well, actually I'll do it right here, I'm going to do the molar mass of aluminum sulfate. So if you don't know how to do molar mass, here's a mini lesson for you. So I'm going to break it down. This is made of aluminum, sulfur, and oxygen. I'm just really doing an atom inventory here. I have 2 aluminums. I have 3 times an understood 1, 3 sulfurs, and I have 3 times 4, 12 oxygens. Now I'm going to look up the masses of each of these elements on the periodic table. Aluminum is 26.98. That is grams per mole. I'm not going to write that because this is just scratch work for me, but do know that that's grams per mole. Sulfur is 32.07 grams per mole, and oxygen is 16.0 grams per mole. So we're going to multiply everything across. 2 times 26.98 is 53.96 grams per mole. I have to write that. It feels wrong not doing it. Sulfur is 3 times 32.07. That is 96.21 grams per mole. And 12 oxygens times 16.0 is going to be a grand total of 192.0 grams per mole. Now, in order to get the molar mass of the aluminum sulfate, I'm just simply going to add these 3 numbers together, and that is going to give me 342.17 grams per mole. I literally had to do all of that work just so I can start this problem. So there's two skills you've already used. You had to know how to write your chemical formulas, and you had to be able to do molar mass. So now let's actually look at what the problem's asking us to do. They're telling me you've got 50 grams of this aluminum sulfate, and they want to know how many individual oxygen atoms is that. They're not asking me how many molecules of ammonium sulfate. They're breaking this ammonium sulfate down, and they want to know how many oxygen atoms. So that's where the new step's going to come in. But the good news is you already know how to start. The first thing we're going to write down is the given, and that is 50 grams of aluminum sulfate, Al2SO4 3. I'm trying to write a little smaller because I'm probably going to run out of room if I don't. Very long line, short line. Now when you've got grams, there's one place you can go, and that's moles. I already know the molar mass of this because I just figured it out. So there are 342.17 grams of aluminum sulfate. I know that's a lot to write, but that's how we do it, per mole. Good time to point out, remember mole is always by itself. And I know that 1 mole of anything has 6.02 times 10 to the 23rd molecules. And in this case, it's aluminum sulfate. Now, just in the interest of space here, normally I would put aluminum sulfate's formula there, but I'm just going to stop it. I would encourage you, if you've got room, to put the Al2 SO43 there. But there's 6.02 times 10 to the 23rd anything's in a mole. So the grams canceled, the moles canceled. If I stop right here, I have calculated the number of aluminum sulfate molecules, like in 50 grams. If I could take all of those individual molecules and line them up, if I stop here, I have figured out how many of those I have. They don't want to know how many molecules. They're saying, how many oxygen atoms is that? It's just another ratio. Per every 1 aluminum sulfate, I have 3 times 4, I have 12 oxygen atoms. So I'm just going to write 12 oxygen atoms per molecule, because I'm going from molecule to atoms. This is the only new step we're adding. Let me give you a comparison. It's probably kind of weird, but let's say I had 10 people, and they were all like identical. I had 10 people. The people, each person is like a molecule. If each person has 2 arms, then 10 people is going to be 20 arms, right? Because there are 2 arms per person. That's kind of the same thing. This is the whole thing, and the oxygen's just a piece of it. There happen to be 12 oxygen atoms per molecule, just like there are 20 arms if I have 10 people, 2 arms if I have 1 person. If everybody has 10 fingers and I have 10 people, 10 times 10, that's 100 fingers. So it's just a ratio between the little part that's a small part of the big part. That's all we did. So anytime they give you a molecule, but they're asking you to break it down into an atom, that's what you're looking to do. They could have given you moles. They could have started you here, and if they would have given you moles, you would have just gone from mole to molecule and then to atoms. It doesn't really matter if they're starting you with grams or moles, but you're going to find the total number of molecules and then break it down into the atoms that they ask you for. Let's just pretend they would have said, how many sulfur atoms is that? Instead of oxygen, they would have asked about sulfur. In that case, you would have said there are 3 sulfurs per every molecule, so you would have had 3 sulfur atoms per molecule. Doesn't matter which one they ask you about. If they would have asked you about aluminum, you could have said 2 aluminum atoms per molecule. You're really just adding one more ratio, comparing that specific element, in this case oxygen, to an individual molecule. So that said, let's just go ahead and calculate this up. We're going to multiply 50 times 6.02 times 10 to the 23rd times 12. Hit equals. Divide that by 342.17, and your final answer is 1.06 times 10 to the 24th atoms of oxygen. So basically what you figured out here was that if you were to have 50 grams of aluminum sulfate and you broke that down into all the individual little atoms and you separated them out and you could count them, you would have 1.06 times 10 to the 24th oxygen atoms. You would never be able to count those in your lifetime, but still it's kind of an interesting little thing to know. That's why we need that 6.02 times 10 to the 23rd, because we could never count a number that big. All right, let's take a look at another problem. We're going to do it exactly the same way. So this problem says, calculate the number of chlorine atoms in 25 grams of phosphorus pentachloride. So first thing we've got to do is dig into our skill set on writing and naming formulas, and we've got to figure out what that phosphorus pentachloride looks like. Now, I recognize that as covalent because it's a nonmetal and a nonmetal. Also, what always grabs my attention is that penta, because we cannot use prefixes in ionics, but we can use them in covalence. So that's telling me this compound has 1 phosphorus and it has 5 chlorines in it. So it's going to look like this, PCl5. So that was pretty easy. And now I'm going to find the mass. So we have phosphorus and we have chlorine. We have 1 phosphorus and 5 chlorines. I'm just taking an atom inventory here. And now we're going to look up those masses on the periodic table. Phosphorus has a mass of 30.97 grams per mole. And chlorine has a molar mass of 35.45 grams per mole. This is my scratch work. A lot of people will just do this quickly in the calculator. I'm just giving you a little extra information. So let's multiply this across. That's going to be 30.97 grams per mole. And 5 times 35.45 is 177.25 grams per mole. We're going to add these together, and when we add these together, we get 208.22 grams per mole. So that is the molar mass of phosphorus pentachloride. Now we're ready to solve the problem. I'm going to try to write a little smaller this time so I don't run out of room. I know a lot of you probably run into that same issue. It drives me crazy. So we're going to start with 25 grams of phosphorus pentachloride. So 25.0 grams of PCl5. Let's get our line in there. We're going to go from gram to mole first. That's really the only place you would want to go from grams. So we already know that phosphorus pentachloride has a molar mass of 208.22 grams per mole. Remember, mole is always by itself. Now grams cancel. Now where are we going to go? Well, if you're in moles, you can go 2 places. You can go to grams, which would be weird because we just came from there, or you can go to molecules. So we're going to go to molecules. Moles by itself on the bottom, remember, because they want to cancel. And we know that there are 6.02 times 10 to the 23rd molecules of anything, in this case PCl5 per mole. We are almost there. If we stop right here, we have figured out in a 25 gram sample of phosphorus pentachloride exactly how many chlorine atoms, exactly how many, molecules we have. If you could like literally line them up and count them. But that's not what they want. They want to know how many individual chlorine atoms. So again, we're breaking a molecule down into an individual atom. Well, I happen to have 5 chlorine atoms per every phosphorus pentachloride. So I'm just going to write 5 chlorine atoms per molecule. Molecules cancel, and we are ready to calculate. So once again, if you've been doing gram mole molecule problems, this is just one little extra step. You're breaking it down one more time, breaking it down from a molecule into a specific number of atoms. So we're ready to calculate. So you're going to multiply 25 by 6.02 times 10 to the 23rd by 5. Hit equals before you hit that divided by. Now divide by 208.22, and you should be getting 3.61 times 10 to the 23rd atoms of chlorine, or you could say chlorine atoms. As long as you've got it labeled, you're fine. I usually like to put what it is at the very end. So really not bad. That's such an easy step. You're just looking at the ratio of the specific element to the molecule. Now I want to put up a problem for you to copy and try. So copy it down, put the video on pause, and this way you know if you've really got it. So here's your question. Calculate the number of iron atoms in 75 grams of iron 3 oxide. So go ahead and pause your video and get that copied, and then we'll come back together and do this last one and see how you did. All right, so let's go over this. Iron 3 oxide. That is an ionic compound, and it also has Roman numerals in it, which means they're telling me the charge on that iron is +3. That Roman numeral of a 3 is them just literally saying iron with a +3 charge. That's a really cool thing about the stock method. So I'm going to write this formula real quick. If iron has a +3 and oxygen has a -2, when you crisscross, you are going to get Fe2O3. So what we're going to do real quickly is find the molar mass of that so that when we're ready to plug it into the problem, we're good to go. So we have iron and we have oxygen. 2 irons, 3 oxygens. Iron has a mass of 55.85 grams per mole. And oxygen has a mass of 16.0 grams per mole. So let's get all this together. That's going to be 111.70 grams per mole for the iron, and it is going to be 48.0 grams per mole for the oxygen. So we're going to add them together real quick. And when we add them, we get a grand total of 159.7 grams per mole. Now we're ready to jump in and solve the problem because we've taken care of all that kind of upfront work. So we're starting off with 75 grams of iron 3 oxide. First thing we're going to do is go gram to mole, because we're going to have gram here because it was up here in this step. That is 159.7 grams of iron 3 oxide per mole. It's so nice when you've already got this figured out, because when you're ready for it and you're kind of just really trucking along, you can go ahead and throw it in the problem. I love that. So grams cancel. Now we're going to go from mole to molecule. So 1 mole is equal to 6.02 times 10 to the 23rd molecules, Fe2O3, barely leaving room for that last step. Again, if you were to stop right here, you would have figured out in that 75-gram sample how many of these you had. Like the whole thing, the whole molecule. These things right here. If you could line them up and count them, that's what you would figure out. But they don't want that. They want to know how many iron atoms this time. Very specifically, iron atoms. And I have 2 iron atoms per molecule. So 2 iron atoms per molecule is what I'm going to multiply by. 2 atoms iron per molecule. Molecules cancel. So we're ready to calculate this up. So multiply everything on the top together, hit equals, divide by 159.7, and you should be getting 5.65 times 10 to the 23rd atoms of iron. And that's all you do. So hopefully that was really helpful to you and some of my students. If you were struggling on that latest review packet, then that's going to be a good thing for you to see as well. And hoping that cleared some things up.